Hi, so this is a little lecture, little video on the theory of LP. And we're just going to state the theory. We don't care about proving the beautiful, beautiful mathematical facts. This isn't a math class. So the big fact, and this is on this material in the pre-reading starts on page 61, in case you want to follow along with better diagrams than what I'm doing. So the big fact is that an optimal point has m variables that are allowed to be greater than or equal to 0, and n minus m variables that are forced to be held at 0. So out of the n variables in the x, m of them are allowed to be 0, are allowed to be positive, and n minus m are forced to be 0. So the special m are called basic, and the others are non-basic. So it's, of course, also possible that there aren't any optimal points. So when we say an optimal point, blah, 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 it means if there is one, of course. Okay, so the rest of so that's just a deeply profound fact. Whoops, sorry about that. What happened there? Rescaled the world. Okay, so that's a really important fact. And on the farm example, if you looked at that in the 2D case, you could kind of see that in action, because the feasible set kind of had these corner points, and those corner points were places where out of all the variables the right number were allowed to be non-zero, and the others were all at 0. This also might remind you, in matrix algebra, if you had a really good matrix algebra class, if you're solving a system, an augmented matrix, and it's got more rows than columns, if it's got m rows and n columns, you can do basically, you can do row operations to get an identity matrix in part of it, and then the others become whatever they want to be, and then these guys are the parameters, and your instructor might have talked about how there are infinitely many solutions. So in that case, we just set the n minus m parameters to any values we wanted and solve for the parameters. So this is the same situation, except because we have the restrictions that all the non-variables are greater than or equal to 0, turns out setting the parameters gives us what we want. So later in the pre-reading, I'll probably, because I have it written up, I'll probably print or put on the website the discussion of the theory, in case you're curious and want to see some of these facts proven, which is probably unlikely. Okay, so now so that's the big mathematical factor playing out of thin air, and everything else we're going to do with linear programming and the simplex method we're going to actually be able to prove pretty easily. So to understand this, we have to think about block stuff in matrices. So we've actually already done this a little bit when we did Straussen's algorithm and we did the fast Fourier transform. We were definitely thinking of matrices as being broken into blocks. But the big fact is that if you take a matrix, say with a coefficient matrix times an unknown variable matrix equals the right-hand side, if you split the coefficient matrix into like 2 pieces, and you can split these, and if we call this block A, B, C, and D, and this block X1 and X2, and this Y1 and Y2, then we can do stuff with these as if it looks like it's a 2 by 2 linear system, but actually maybe A is 100 by 100. So it doesn't matter. it's still true that ax1 plus bx2 equals y1, and cx1 plus dx2 equals y2. So, and you can also do row operations and things in blocks. So we'll be using that in a very nice way to derive the results we need. Okay, so our tableau looks like this. Our tableau has the costs across the top, and it's got the coefficient matrix A, and it's got the right hand side. So our original setup here, let's see, I'm forgetting. Yeah, so we've already talked about putting in the Z, right? Oh, maybe we haven't. Just a second. Oops, sorry, I got ahead of myself. So a really important idea is that we can put in the C value as another equation. So we introduce a new variable we call Z traditionally, and Z is equal to C transpose X. So we're just giving really a name kind of to the quantity, C transpose X. But the important idea is we can turn that into a nice equation by saying C minus C transpose X equals 0. So so what we're doing is adding, we've got our variables x1 to xn, and we're adding a variable z. So the variable z in the first row looks like this. So we have a coefficient of 1, because right, it's got a coefficient of 1 down there, and then it's c1, cj, and then cn, and the right hand side is 0. So in the usual augmented matrix way, we've got 1 times z plus c1 times, oh, but these are minus, right, because we had to subtract it from both sides. So we can do that. And then our equation here says that ax equals b. So the coefficient matrix big A multiplied by the unknowns x gives us the right hand side b. And the x greater than or equals 0 will just enforce by the nature of the algorithms we do. It's not, we can't express that nicely in terms of the matrix. Okay, so the key idea is that we pick actually m of the xj's to be basic. And we're going to rearrange things. We're going to rearrange the world so the basic variables are the xb's, and we'll write xb transpose to lay it on its side. There's m of those, and then the rest of them we'll call xn. So those are the non-basic variables. And then this last spot we sometimes denote as the right-hand side. Okay, so that's just labels for which variables correspond to which columns, yeah. And then here, and then we also have z as one extra guy. And so the first row has, like we were saying, 1, and then we call this minus cb transpose. So this is all really just notational, which minus cn transpose. So we're and then 0. So that equation says that z minus the cb, the coefficients for the basic variables, times the basic variables minus the coefficients for the non-basic variables equals 0. And then in the coefficient matrix, we're going to break into a square matrix B. So there's m rows and m columns, because xb has m guys in it. And then we have this non-square, probably still often wider than it is tall, guy we call n, capital N for non-basic. And the right-hand side is B. Okay? Now, the amazing thing here is, let me get rid of that. And notice that this column is all zeros, because that just says the z we introduced here for the first row, that's the only place it occurs. It's kind of a fake variable. Okay. So, but to make it all one big happy matrix, we do this. So this is the augmented matrix with its right-hand side and the coefficients, as usual when you do this kind of thing. Okay, so now we're going to do block row operations. Oops. I'm just going to move this up. I hope that works. Okay, and so what are we going to do? Well, what we're going to do is, first thing we're going to do is we're going to multiply this row. So we think of this as, in the notes I put quotes around it. So this is row 2. So we just call this the 0 vector and b, so it's just 0, b, n. So we call this guy 0, b, n, and little b. So we think of that as a row, and we just multiply that whole row by b inverse. So if we do that, and I've got to write down these guys, recopy them, because this ain't no smart board. So we got 1 minus CB transpose minus CN transpose and 0. And underneath that we've got, so what is B inverse times 0? Well, B inverse times 0 is just 0. So we write that. And what is B inverse times B? Well, that's why we did this. B inverse times B is just the identity matrix. So this is just a notationally nice way of saying we do row operations on this matrix, whatever it takes to convert this to the identity. You know, put 1s on the diagonal and 0s everywhere else, like you're totally familiar with, hopefully. Okay, and then this next component is B inverse times n. So that just is capturing the fact that we do the same things to n that we did to b. So as b is converted to the identity, n gets converted to b inverse n. And finally, the right-hand side in the same way is capital B inverse little b. Okay, so that was exciting. So this corresponds, producing the identity matrix we call pivoting, or pivots or whatever. All right, so now that gets us up to there. Okay, so now we want to do the next step of turning this all into a nice situation, which is to add a multiple. We want to add a multiple of this row to this row. And the multiple we're going to add is CB transpose. So we're going to multiply each element here by CB transpose and add them to the corresponding spots up here. So if I can move this down one more time, this should work out well. Okay, so what do we get? Oops, pencil back. So what we get in the top, so it's 1 plus CB transpose times 0. But of course CB transpose times 0 is 0, so in the Z column we've still got 1. Okay, what about in the columns for the basic variables? Oops, I'm probably going to regret that. Okay, in the next column here, we get CB transpose times the identity added to minus CB transpose. And the point of that, of course, is you just get a 0 transpose. You get zeros in all those spots, which is why we're doing this operation. Okay, and now here in this column, these columns for the non-basic variables, we get CB transpose times B inverse n added to minus CN transpose. So we get, I'll write this on the left because it feels better that way. So we get CB transpose times B inverse n, and then we've still got, that's added to the minus CN transpose was sitting there. And in the upper right corner, we get something that won't fit because the spot's too small. Even on the notes when I shrunk it way down, we get CB transpose times B inverse B added to 0, which is just CB transpose times B inverse B. Okay, and then this part just sits here. So what does this tell us? It tells us that when we pick some basic variables, and in fact the software we'll use, the manual simplex, will keep track of these pivot operations. So if you pivot in a column, it's going to register that as the basic variable for that column. And Z is always viewed as the basic variable for the first row. So these tell you which variables have been pivoted on, which ones are the special basic ones for that row. So there's M rows, and each one M real rows, and each one has a basic variable for itself, which changes over time. Can change over time. Okay, so this all says, well, what does it say? These equations, if we multiply it out, remember these variables are actually in a column, and they're being multiplied by the coefficients. So however you want to look at it, this says that 1 times Z plus 0 transpose times the XB's plus CB transpose B inverse N minus CN transpose, that whole mess, times the XN is equal to CB transpose B inverse B. So the exciting thing here is we've either pivoting, we've multiplied the non-basic variables, the basic variables by 0, and we've, in this mess, will matter later, but for right now we're setting all the non-basic variables to 0. So the equation says simply that Z equals CB transpose B inverse B. So Z is the variable that's always telling us our objective function. And there's nothing weird about this either, by the way. These are the coefficients of the basic variables, and they're multiplied by the right-hand side values. Oh, and the other thing, if you look at the second equation, it's the second row. It says that I times XB plus B inverse N times XN is equal to B inverse B. So if XN is 0, and the identity times anything, it just says the basic variables are equal to this. So when you look in the tableau, this right-hand last column is really important. The upper right corner number tells you the current value of the objective function, and these guys tell you the current value of the basic variables. And you know the current value of the non-basic variables because they're always forced to be 0. Okay, so that is some really profound observations, and hopefully the matrix algebra notation hasn't upset you. And we'll come back and keep playing with these things as we go on, so they'll sink in. Okay, so now we're now set up to where we can do a brute force approach to solving the linear programming problem. So the brute force approach is maybe kind of obvious. You just try every choice of M basic variables. And you see two things. See if it's possible to do that, and we'll see what that means in a second. And then we'll see if it gives you a feasible choice, and then we'll notice what's the Z. Okay. So if you had variables x1 and x2, and the column for those guys look like 3, 1, minus 1, and 6, 2, minus 2. If you went in and tried to pivot like here, then that would be fine, and would convert this to 0, 1, 0. But this column would also become 0, 1, 0. So you wouldn't be able to go back and pivot somewhere else in these rows because you'd have zeros. So sometimes it's not possible. That will very rarely, if ever, come up in our examples, but it's a mathematical possibility. Okay, and when you pick some variables to be basic, and you do the pivoting, there's no control over this B inverse B. So if any are negative, it's not feasible. So this isn't a surprising thing. In the farm example, if you had actually done where these various guys crossed, some of them would have crossed, some of them crossed in places like these two lines cross on the wrong side of this guy, so that point's just not a good possibility for a solution. Only some of the places where two of the lines intersected were actually reasonable choices. Okay, and finally, so over the ones where we can actually do the pivoting we want, and where all the right-hand side numbers are positive, non-negative, sometimes they can be 0, but we kind of like them to be positive, then we check to see which one has the best. So I'm going to just do a little example of this to make it clear, and if I could embed the manual simplex video or something in these iPad videos with my software, that would be great, but I'm just going to have to put up the log of what happens and talk about it. Okay, so let me go get the log that I previously prepared, if I can remember how to do that. So we're going to bring in a file. Okay, howdy. So here is a series of things for the problem. So I'm doing here embedded exercise 38, if you want to look on page 64. Is where the problem itself is defined. So basically we can read right off the matrix what's the so this says the objective function, so z is equal to blah blah blah. So if we add these back to subtract these from the other side, it says z equals 3x1 minus 2x2 plus 4x4 3 plus 7x4 equal, right? Or by moving them over, we're saying z minus 3x3 plus 2x2 minus 4x4 minus 7x4 equals 0. Okay? And here are the constraints, which of course the z doesn't appear in the constraints. And it says, this one says x1 plus 2x2 minus x3 plus 4x4 equals 8. And this says no z, 6x1 plus x2 plus 3x3 minus x4 equals 12. If you look on page 64, that, excuse me, that is exactly the problem we have. And of course, we're assuming, as always, that the variables are non-restricted. So, looking at this, to do the brute force method, we make ourselves a little chart. And in the chart, we're just going to say the basics are, we can do x1 and x2, we can do x1 and x3, x1 and x4, x2 and x3, x2 and x4, or x3 and x4. So I forgot to say before that there are n choose m choices. In general, this is a very big number. It's the number in Pascal's triangle as you head way the heck down. And for each one, you have to do, so for each one of these choices, you have to do some pivoting work, which could be as much as n times m, because that's how big the coefficient matrix is. It's m by n. So when you change the basic columns, the b into I, you might do this much work. Sometimes it's less work, but no, actually it isn't. It's if this is the number if things go well, as we'll see in a minute. So what I do, for each one of these, I want to know if it's possible, and it turns out for this problem, as usual, all of them are. So we'll just say check, 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 check. But we wouldn't know that till we tried. And then we do feasible, and then we'll write down the z. So if it's possible and feasible, then we write down the z, and then the winner is simply the best z. So we start out and we say, let's pivot for here, which to bring in x1 basic, and then here to bring in x2. So with the software, I simply use the arrow keys to move to this spot and hit P. And then I use the arrow key here to move here and hit P, and then I'll see this matrix on the screen. So this is what we were calling B. This is big B inverse N. This is the zeros after we've added this row to the top row and so on. So these crazy numbers are that crazy CB transpose B inverse whatever, very complicated. This is the current objective function value. So, but the main thing we have to look at here is these guys. These are the right-hand side values. In other words, x1 is equal to 1.45 and x2 is equal to 3.27. So those are both positive, so over here for this row we say yes, this is feasible, and we go ahead and write down the minus 2.18. Okay, so now we could pivot on any of these spots. In general, we've got 8 spots from which to choose. The order doesn't matter. If I'd pivoted here and then here, I would have got exactly the same right-hand side, but it would have been permuted. I'd have x2 here and x1 here. So we kind of try to keep our identity columns going from left to right to not get too crazy. So my next idea is I want to get x1 and x3, so I just move over the arrow over here and hit P, and that gives me this identity column to go with this one for x1 and x3. Now this one has, so this is infeasible. So we just put a dash there and we don't have to do any further work. Then I move over to here and hit P, and to get this column to go with this column to try out x1 and x4. Those guys are feasible and get a score of 16.8. So yes, and 16.8. So that's pretty good. Then now I have to do a little more work than just adjusting one column. So I pivot on this guy to make this identity column, and then I'll pivot on this guy to make this identity column. So that gives me, I've got x2 and x3, and when I do that, I get the right-hand side values for x2 and x3 of positive, non-negative anyway, and so this is feasible, and I get minus 1.14. So that actually, so far the winner is the 16.8, by quite a margin. Okay, then I've got x2, so I go over and pivot here to get x4. Oops, oh dear, this is not good. Damn it. I don't think this is going to work. What's going on? Okay. So let me just comment. We're almost done, and things are screwed up. So I continue like this, and I get x2 and x4 has a negative, so that one is not feasible. And then down here, it turns out, I'll just show you this and then put it back. It turns out that this last tableau has positive values, 5.09 and 3.27. Right? Oh, great. Oh, I guess it's scrolled up enough now. Okay, so the x3 and x4 has 2 positive values, and it's got a z-value of 43.7. So this is feasible, and the z-value is 43.27. So because this is the winner of all the feasible ones, it's the biggest. So this is the winner. So the optimum is what? Well, it's x3 equals 5.09. x4 equals 3.27. And off to the side, we state the obvious that x1 equals x2 equals 0 because they're non-basic. And the z, the objective function value, is 43.27. So that is all there is to the brute force approach to solving a linear programming problem. And we will you'll play with it a little in the lesson, but a little bit is enough because it's very inefficient. So the next thing we'll do is explore the simplex method, which does these steps somewhat more efficiently. Thanks for listening.